Okay, in this video I'm going to do a quick review of what we've already talked about in class, being the defining the coefficient of restitution in terms of the impulses that happen during an impact process, and then we'll look at three examples. So we have two particles that are traveling in the same direction, and so their impact direction is quite clearly going to be horizontal. Particle 1 is catching up to particle 2 and it will eventually hit it. Then they will come to a maximum deformation where they have impacted to the maximum and they're traveling at the same speed. Then finally there'll be a restoring process after the impact in which the right-hand particle is traveling faster than the left-hand particle because of the impact. During the deformation period, particle 1 will be catching up to particle 2, and there will be a force of deformation. Force is changing with time, okay, but there will be an impulse because of that deformation force. During the restoration period, where they're transitioning from moving at the same speed to particle 2 moving faster than particle 1, there's a restoration impulse pushing the two bodies apart and separating them. And that restoration impulse is acting equal and opposite on each of the bodies. We will define the coefficient of restitution in terms of those restoration impulses and the deformation impulses, and because we may not get complete recovery or complete recovery of the energy, our restoration impulse is generally less than the deformation impulse. So taking the ratio of those two terms, our coefficient of restitution is typically a number that's less than 1. It's never bigger than 1 and never smaller than 0. Writing our impulse integrals in terms of these velocity changes approach to being connected, then from being connected to separating. We can do that for body 1. We can also do that for body 2, recognizing they have the same E, and recognize that they were sharing the same velocity at maximum impulse or maximum impact, sharing that same velocity of V0 that we don't care about. What we're left with when we combine these equations is an equation involving starting and final velocities of both, and that's our coefficient of restitution equation, which is the velocity of approach, 1 moving faster than 2, in the denominator, the velocity of separation after the impact with 2 moving faster than 1, causing those both to be positive numbers. An elastic impact where our restoration impulse is the same as our deformation impulse would give us an E = 1, no energy loss. A pure plastic impulse, which means hit and stick, would give us an E value of 0. Now, it's also possible to have impacts where the bodies come in from differing directions, and we have to decide where the line of impact is and where the line of impact is not. So what we have is this body 1 coming in from this direction, body 2 coming in from this direction. They will arrive in a certain configuration, and it certainly doesn't have to be this configuration. They could have arrived side by side, making the horizontal line the direction of the impact. They happen in this picture to have arrived one on top, one on the bottom. They could have arrived at almost any angle. It's fairly amazing that they arrived top and bottom. But body 1 will come in, go through the impact along the vertical direction, and body 1 will leave. Body 1's velocity parallel to the impact direction will change. We can see it's heading downward, now it's heading upward. Body 1's velocity perpendicular to the impact direction will have absolutely no change. It will, so in this case, the x direction of body 1 before impact is the x direction of body 1 after impact, no change. Same is true for body 2. X direction of body 2 before impact is the x direction velocity of body 2 after the impact, no change. But clearly, body 2 is moving up, parallel to the impact direction before the impact, and now it's moving downward. It has a negative velocity after the impact. Okay. Let's look at one particular kind of impact, which is a fairly lightweight object bouncing off of a supermassive object. And let's go to a zoom level where we can read this problem. The problem statement says tennis balls are usually rejected if they fail to rebound to waist level when dropped from shoulder level. If a ball just passes the test as indicated in the figure, determine the coefficient of restitution E and the percentage N of the original energy loss during the impact. Picture explains it maybe even better. Tennis ball is dropped from shoulder level, and for it to be acceptable, it must return to waist level. Here we have the definitions of heights for shoulder and waist level for this particular person, and we're going to presume that this ball passes this test. And what we want to learn is what is the coefficient of a ball that passes this particular test. And so let's zoom back out to the right level. That looks right. So we're going to define H as 1600, which is the height before the impact, and H prime is the height after the impact. Now, this equation, V equal the square root of 2gh, we've seen before. It comes from the equation 1/2 mv squared is equal to mgh. Bring the 2 to the other side, take the square root of both sides, and cancel the m's. And this is just an energy equation where velocity turns into height. Okay, and so we'll have this equation for velocity and height before the impact. We'll use prime notation to represent right after the impact, so we'll have this velocity immediately after the impact. So at this point, the ball has fallen through height h and achieved a velocity v just the instant before it hits the ground. This is the instant right after it's left the ground. It has achieved no height yet. And so we use energy in this problem to tell us the speed of the ball on either side of the impact, because clearly it had no speed at either of these 2 points, but it's acquired speed right before impact. It will have speed right after impact to bring us back up to the 1100 height. In this problem, since there are only 2 unknowns, the velocity of the ball after impact and the velocity of the ball before the impact. But the E equation usually has 4 quantities in it. What were the other 2 quantities? Velocity, in this case the velocity of the Earth before the impact, and the velocity of the Earth after the impact. We will treat these supermassive collisions, lightweight to supermassive collisions, as if the velocity of the supermassive object undergoes absolutely no change. That's not precisely true. There is a minuscule, absolutely minuscule change in velocity, which produces a non-minuscule change in momentum. Okay, but we're not going to even use the momentum equation, because it would maybe mislead us unless we actually found the velocity change of the Earth. We're simply going to use coefficient of restitution when we have lightweight object impacting supermassive object. And plugging in the velocity equation, the velocity terms, and instead substituting square root of 2gh for the numerator and square root of 2gh prime for the denominator, and canceling this 2g's, leaving the square root of h prime over the square root of h, and therefore square root of 1100 divided by square root of 1600, we have a 0.829 coefficient of restitution, found only with velocities computed by energy, and we did not have to use momentum in this case. We never will for collision with a supermassive object. Then to calculate the percentage of energy lost, and we clearly lost some, and it might be tempting to say that this is about a 0.83, so we lost about a 0.17 energy, but this is not an energy equation, this is a velocity equation. So we actually have to calculate energy carefully. Okay, and energy that we started with was the ball at the height mgh. The energy that we ended up with was the ball at a lower height. So let's take our starting energy minus our final energy divided by the starting energy, multiply by 100% to get percent energy change, and plugging in those H numbers, we get a 31.25% loss of energy because of that impact. So we lose 31% of our energy when a good tennis ball bounces. Okay, let's look at another oblique impact. This problem is a little bit turned around, but it's worth looking at. Let's zoom in to where we can read the problem, and then we'll take a look at the picture. 2 cars, A and B, each having a weight of 4,000 pounds, collide on the icy pavement of an intersection. The direction of motion of each car after collision is measured from snow tracks as shown. So we'll know the direction after collision. If the driver in car A states that he was going 44 feet per second, which is 30 miles an hour, just before the collision, and that after the collision he applied the brakes so that his car skidded 10 feet before stopping, determine the approximate speed of car B. Just before the collision. Assume that the coefficient of kinetic friction between the car wheels and pavement is 0.15. Note the line of impact has not been defined. However, this information is not needed in this solution. This says the solution is going to maybe be a little weird. We're just going to have to see what we can say that's true and see what turns out. Okay, so we have our picture of the problem, in which we have car A traveling into the collision point. We have car B traveling into the collision point, both at the same speed. And what is interesting that we do know, which may eliminate the need to use one or more of the equations we have in our arsenal, we know the angle of this one, and we're going to know something about energy of car A because it slid under friction a certain distance. And we know the angle with which car B is leaving the impact zone. Knowing those two angles will probably substitute for some equation we might otherwise have to use, and in this problem it will almost certainly substitute for the coefficient of restitution equation. So what we're going to do is sort of work backwards, and there are three states to the problem. There's velocities right before the impact, there are velocities right after the impact right here, and then there are velocities of car A when it finally comes to a stop. So there are three states: right before impact, right after impact, and car A comes to a stop. Now in theory, if car B didn't put on the brakes, car B would never come to a stop. That's not true, of course, but we don't have any data on the speed of car B after the impact. But we'll use energy to see what we can learn about car A from right after impact to car A coming to a stop. Okay, so find the velocity of A just after the collision. We're going to use energy, conservation of energy. No, not conservation of energy, because we have friction. We've left off the potential energy terms because there are no springs and there's no gravity involved in this one. We'll say that the kinetic energy plus any work done in transitioning from state 1 to 2 is equal to our final kinetic energy. Final kinetic energy should be 0 because we came to a stop. The initial kinetic energy, based on the claim of the driver, is 1/2 m times VA squared. Now this is the velocity of A right after the impact, and we don't know it, is equal to, or subtracting away, work done by friction. Those two should cancel and add to 0. Work done by friction is m, 4,000, which is also N, the normal force, times mu, 0.15, times the distance traveled of 10 feet. So we have energy of velocity right after the collision consumed by friction, bringing us to 0 velocity, and that gives us a velocity of A at state 2 in the problem of 9.829 feet per second, which is right after the impact is over. Now let's write momentum equations through the impact, from the pre-impact side to the post-impact side. And what we're going to do is we're going to look at the x direction only, because we are allowed to do that. We can pick directions. And we're going to say that, first of all, looking back at the picture, we have pre-impact, car A is the only one with any x direction momentum. Car B only has y direction momentum. After the impact, each of the cars has x direction and y direction momentum. And we know the angles, we know the masses, and we know a little bit about the velocity of car A. And so, car A enters the impact zone with a speed of 44 feet per second, so that's its momentum. Car B enters the impact zone with 0 momentum in the x direction. Car A leaves the impact zone in the x direction, having mass times its total velocity times the sine of the 40 degrees, that's the direction it's leaving. And then car B does have some x direction momentum, which is the mass of car B, times the velocity of car B right after the impact, times the cosine of 30 degrees, that's the angle with which it is leaving. This is in fact a one equation, one unknown. So momentum in the x direction only Now that we know the momentum of car A right after the impact, allows us to solve for the momentum of car B right after the impact, which means we can solve for the velocity of car B right after the impact. So VB2 is 43.5 feet per second. Now, the next thing we can do, and to write something that's true, is some momentum in the vertical direction across the impact. And so in the vertical direction, car A has only x direction motion pre-impact, so its momentum in the y direction is 0. Car B's momentum of the y direction is mass times velocity. It is heading in the negative y direction, and so we are going to put a minus sign in there. We do need to pay attention to our signs. Okay, so this is the momentum of car B before impact, and then y direction momentum of car A and B after impact, both are negative, would be an mv cosine of 40 degrees and an mv, and we had already solved for that v just a moment ago, times the sine of 30 degrees. Putting all of those together, we get that car B pre-impact had a velocity of 29.3 feet per second, or approximately 20 miles per hour. We were able to solve this problem without using the coefficient of restitution equation because we were given a large amount of extra information, and that is the angle that each one left the impact scene, and we were given enough energy information to determine the velocity of this one right after the impact, making coefficient of restitution unnecessary. And since we didn't know the line of impact back then, we could not have worked with coefficient of restitution anyway. Moving on to another problem. Let's read the problem statement by zooming in a bit first. Looking at the picture, we see a ball is going to hit a block, and the block's going to swing up to a certain height. Yes, I did have that on the screen properly. Alright, so a 2 kilogram ball is thrown at the suspended 20 kilogram block with a velocity of 4 meters per second. If the coefficient of restitution between the ball and the block is E equal 0.8, determine the maximum height to which the block will swing before it momentarily stops. Zooming back to the right amount. Now, we worked a problem something like this before, but this problem, that earlier problem, was a hidden stick problem, in which a bullet became embedded in a box of sand, and they stuck together, moved at the same velocity, and then the box moved upward. And we used the height change of the box to determine the speed of the bullet. In this case, we're actually going to have a bounce between the ball and the block. Okay, but we will still have some motion of the block, and it'll swing up a certain height, and that's what we want to calculate. We were given the value of E of 0.8, so it's not going to be a hidden stick, and it's not going to be in conservation of energy, so we have to work this problem carefully and properly. Clearly our direction of impact will be in the horizontal direction. So we are going to write momentum across the collision, and we are going to write coefficient of restitution across the collision. And so momentum across the collision says pre-collision we have a ball moving at, is a 2 kilogram ball moving at 4 meters per second. And the block has mass, but it had 0 velocity at that point. And then after the collision, we have our 2 kilogram ball moving at an unknown velocity, and our 20 kilogram block moving at an unknown velocity. This is one equation, 2 unknowns, and so we need another equation if we're going to be able to solve this. And so our coefficient of restitution equation comes to the rescue. And our coefficient of restitution says the velocity of the block minus the velocity of point A of the ball A after impact. So this one is bigger than that one, more positive than that one. And this would be velocities after impact. These would be velocities before impact. Velocity of the ball before impact, velocity of the block before impact. We know those. That's a 4 for the ball and a 0 for the block. And we know coefficient of restitution is 0.8. So this equation, again, is a 2-equation, 2 unknown problem, but it has exactly the same 2 unknowns as our earlier equation. So we can solve those 2 equations, 2 unknowns, for our velocity of A post-impact is moving back to the left at 2.545, and the velocity of B moving to the right after the impact at 0.645 meters per second. And I think this fits our intuition that says if a fairly lightweight ball hits a very heavy mass, the ball will bounce and continue to move faster. The heavy mass will move slower. Now that we know the velocities of both pieces immediately after the impact, this is the velocity of the block right after the impact, but before it's changed its height at all. So we're going to be able to write a conservation of energy equation that says our velocity of the block turns into height energy of the block. So 1/2 mv squared plus 0 for the ball, let's see, plus no kinetic energy to start is equal to no potential energy to end the problem plus nothing but kinetic energy to end the problem. Potential energy, I said this wrong. Kinetic something, potential 0. Kinetic 0, potential something. And h is the only unknown. We don't have the 1 minus cosine term in here for the swing problem because we don't care about the angle, we just care about the h in this case. And we get an h of 0.0218 meters or 21.8 millimeters, not a large height change, but not 0 either. And that ends this discussion on chapter 15. And I will post this video, and then I'll be posting another one on the beginning of chapter 16 shortly.